Welcome to the second part of Lecture 2, so 2B. We are going to talk about molecular dot structures. So we've talked about how to do atomic dot structures, and now we're going to look at expanding that a little bit and moving on to how do we do dot structures for entire molecules. So when we're doing dot structures for molecules, we find reasons we want to do them is because the dot structures themselves are very useful for helping to determine the bonding that is present in a molecule. And if we can determine the bonding that's present, we have a good chance of determining its reactivity, where reactions will happen, how reactions will happen, where will things bond through a reaction. And so this is really a very powerful tool. And a lot of times it's the starting point in determining what kind of products you're going to get out for different reactions. The other thing it can help us do is to lead to shape prediction. And shape prediction in chemistry is very important if you are in something like a medicinal chemistry field. If you're familiar with the lock and key idea of how drug interaction occurs within the body, all of that is due to shape of the ends of molecules or the middles of certain molecules. And yeah, we'll see some ideas of how that comes about. So shape prediction gives us an idea of chemical behavior, like we just talked about. So there's a series of steps that we need to use in order to draw dot structures for molecules. Not quite as easy as what we did for the atoms, and that makes sense. Molecules are more complex than atoms. So the things that we do with molecules tend to be more complex than what we would do for atoms. And so we're going to look at this series of steps. And the important thing with this series of steps is that we do them in order. If you do them in a different order, you say, well, I'll just do these steps in a different order, you're not going to get the same answer, and your dot structure will most likely not be correct. So the first thing that we're going to do is we're going to calculate just a total number of valence electrons. Now, the reason we do that is we have a collection of atoms that we're going to make a molecule out of, and each of them has a certain number of valence electrons. They all want to try to achieve their octet, to have those 8 valence electrons count around them. That's why they form ions when they're doing ions. But here, when we're doing dot structures, generally we're going to use them for covalently bonded atoms. And so what we're going to do is we're going to take all these valence electrons, we're just going to put them into a big pot and say, okay, these are the electrons we have available. We have to fill all of the octets of all the atoms with this number of electrons. Now, the one exception to that, of course, is the hydrogen atom. Anytime you attach a hydrogen atom with a bond, it feels like it has 2 electrons in it because each of those covalent bonds represents 2 electrons. And so in that case, we just have the 2 electrons around hydrogen. That makes it look like helium. It feels like a noble gas, and it's happy. So hydrogen, once it makes its bond, it's perfectly happy. Okay, so we've added up all of our valence electrons. We want to write that number down. The next thing we want to do is we want to draw the molecule, attaching each atom to a single central atom with a single bond. Now, you may ask, what is the central atom going to be? Generally, it's the first non-hydrogen atom listed in the formula. Okay, so when you look at a chemical formula, if it's written in a kind of an accepted manner, the first, as you read left to right, the first atom that is not hydrogen is going to be the atom that is in the center. So we put that atom in the center, we attach all of the other atoms to it with a single bond. Now, the other thing that I didn't put on here is you do have to keep account of all of the electrons that you've used. And every time that you add a bond, you've used 2 electrons. And so when you attach all of those other atoms to that central atom, you have to count the number of single bonds that you've put on there and multiply by 2 to get the number of electrons you used to make those single bonds. And you want to subtract those from the original total number of valence electrons. Okay, so now you've got a certain number of electrons that you have left to try to complete everybody's octets in there. So the first octets that we're going to fill are the outer atoms. So you have the inner atom, the one in the center, And then you have all of the outer atoms. So we're going to add lone pairs to the outer atoms first, and we're going to complete their octets. Now, it's very important. We're going to complete their octets. We don't worry about how many valence electrons does the lone atom have, okay? Because lone atoms have a certain number of electrons around them, but when they form a compound, they do so to fill their octets. So we're going to add lone pairs to those outer atoms to complete their octets. If after you've finished the octets of the outer atoms and you still have electrons left over, you will add them as pairs to the central atom. And this is very important. Whenever you're adding electrons here, you add them as pairs. You don't add singles in different places. You just add them as pairs. Okay, now, if you put all your electrons around the outer atoms and you have no electrons left, which happens a lot of times, sometimes you will find that your central atom does not have an octet. And if that happens, then you have to start forming multiple bonds with one of the outer atoms or more of the outer atoms, or it may need to form a double bond or a triple bond or whatever it takes. So we'll look at some examples to see how to do that. Okay, so here's some examples that we're going to go through. Methane, CH4, water, H2O, COBr2, and ClF2-. I will go through those in a separate video. I will post the link to that along with the link to this video as well. So you will see some example videos with dot structures. Another example of something we'll look at is something called resonance. When we're looking at resonance and we look at the examples that we just did in our link there, we may assume that all electrons that get shared between two atoms are localized. And when I say localized, that means that those electrons remain only between those two atoms. And this isn't always the case. Okay, this isn't always the case. So what can happen is that you have molecules where we have different options on where to place other pairs of electrons. So if we reach a place in our dot structure where we have a choice onto where to put a double bond, and we can put it between this atom and this atom, or this atom and this atom, or this atom and this atom, we have a situation where we have something called resonance. Okay, another term for resonance is delocalized bonding. And delocalized means that a pair of electrons does not have to exist just between two atoms. It can exist between many different pairs of atoms. So when we're looking at an actual structure, there's lots of ways to look at it. We can look at it as a compilation of all of the different resonance structures, which sometimes you'll see, or we can look at it in terms of a hybrid of all of the various structures. And anytime you have delocalization of the bonds, it lowers the energy of the molecule. And so that's why a combination of all three of the structures is energetically more preferred than just 3 or 4, however many different individual structures you have. So here's an example of ozone. So we've got a structure on the left there where we had a double bond over here on the left, and on the right-hand structure we put the double bond over here on the right. Okay, and which one is correct? Well, they're both correct. They're actually both equivalent. And so if we're looking at resonance, we can show that we have two different forms like that. That's one way of showing all of the resonance forms. Or you can also show it with a dashed line. You can kind of see right here and right here, a dashed line that indicates that that bond is actually a partial bond between all three of those oxygen atoms on there. So that would be called a resonance hybrid structure. So we'll look at another example of resonance here using carbon dioxide. Carbon dioxide is a great example of resonance, and so I will post a video on that as well. Now, when we're doing resonance structures, sometimes we reach a position where you can form two different resonance structures between different types of atoms. And so, when we do our carbon dioxide, the double bonds or your multiple bonds are going either between carbon and oxygen or carbon and oxygen. Well, those are the same. In an earlier example that we did for COBr2, we saw that we put the double bond between the carbon and the oxygen. We did not put any resonance forms between the carbon and the bromine. Now, there's a reason that we did it that way, and the way that we figured that out is using something called formal charge. I just said all those things, so we'll just skip those bullets for there. So what we really use formal charge for is to determine which atom can best handle a multiple bond. Okay, it tells us which structure is going to be preferred by the molecule when you have resonance. Not all resonance structures are equivalent in energy, and so formal charge helps tell us which one is going to be preferred. Now, when we're doing a formal charge calculation on resonance structures, it seems like kind of a tedious process, but the math itself is extremely simple, nothing more than adding and subtracting. So when we're looking at formal charges for resonance structures, we need to calculate a formal charge for each atom in each possible structure. So if you have a large structure, it's a lot of calculations, but again, it's nothing more than simple adding and subtracting. Actually, it's pretty much all subtracting. So how do we do this? So the first thing that we do is we take a look at the bonds that we have for a single resonance structure. For all of the bonds that we have between two atoms, we split the electrons in the bond. Half of them get assigned to one of the atoms that are in the bond, and half of them get assigned to the other atom that are in the bond. That's nice and easy, right? Okay, and then we look at the lone pairs that we've assigned to the atom. Okay, and they belong to the atom that we put them on. Okay, so if we look at something like water, we saw that water had two lone pairs on it. Both of those lone pairs on the oxygen belong only to the oxygen, and so we only count them for the oxygen. And so our final calculation for formal charge is we take the number of valence electrons that we expect for a particular atom, so something like oxygen would be 6, minus the number of electrons that we have assigned it to the atom in the molecule after we've split the bonds and assigned the lone pairs. So we just take number of valence electrons minus number of electrons we've assigned it, and that gives us the formal charge. Okay, and when you look at all of the formal charges of all of the different atoms in a structure, the preferred structure is going to have all of the formal charges as close as they can get to 0. Now, one thing you have to make sure of that you calculate to find that you've calculated your formal charges correctly is that the sum of all the formal charges should add up to the overall charge on the molecule. If they add up to something other than the overall charge on that molecule or ion, then you've calculated your formal charge incorrectly. Okay, but when you look at all of the formal charges for all of the different atoms, you want to see how close are all of those charges to 0. And the preferred structure has the charges closest to 0. Okay, now occasionally what you'll get is you'll have more than one structure with the same set of formal charges, but they might be on different atoms. And if this is the case, then the structure that has a negative formal charge on the more electronegative atom will be preferred. And I will show you an example of that in a video. Okay, and there's what I mentioned earlier. Okay, so here's some examples. We're going to look at carbon dioxide. We're going to look at the OCN minus ion, and notice it says bonded in this order. So in this case, the oxygen's bonded to the carbon, carbon's bonded to the nitrogen. So the carbon here is actually the central atom in this ion. That's why I very specifically said bonded in this order. If I ever give you a molecule or ion where the first non-hydrogen atom is not the central atom, I will tell you which one goes in the center, or I will give you the order in which they are bonded. Oh. We're going to go back to that real quick. So look for these examples done again as a separate link, as a YouTube video, and then you can see how we use formal charge and how we calculate it. Now, sometimes we will see molecules that need other than octets. So we talked about filling the octets of those outer atoms, filling the octets of the inner atoms. The octet is a good general rule, but we do have exceptions for different elements. Anytime we have beryllium, which is actually fairly rare, but beryllium prefers to be surrounded by 4 electrons rather than 8. It's kind of unusual, but it's just the way it goes. Boron is also a strange element. It prefers to have 6. It is capable of having 8 around it, but it is actually more stable when it just has 6 electrons around it. Now, these are good just to kind of tuck in the back of your mind for knowledge. This is not something I would test you on. I would not give you a boron compound and then mark you wrong because you didn't put 6, instead you put 8. Okay, so again, tuck them in the back of your brain. I am not going to test you on any types of exceptions like that. Now, other things to keep in mind is anytime you have a nonmetal that is phosphorus and later in the periodic table, it can form additional bonds when we are doing dot structures. And these are something that are called expanded octets. When I say additional bonds, that means that we can go over 4 bonds to it. So that means it can hold more than 8 electrons. It can also form 4 bonds and still have some lone pairs, which means it will have larger than an octet on it. And here's a couple of examples. We have arsenic pentafluoride. You can see that the arsenic has 5 bonds to it, so it's got 10 electrons. So we've got these guys just right here. So our 1, 2, 3, 4, 5. So that's going to be 10 electrons associated with that arsenic. And for the sulfur, we see the sulfur has 6 bonds to it. Each of those bonds count as 2 electrons to that sulfur. And so that sulfur actually has 12 electrons around it. So we call these expanded octets. The other thing that we can also have are odd numbered electron species. These are not terribly common, but they do happen in certain chemical fields, especially if you choose to study atmospheric chemistry. Atmospheric chemistry occurs, you get stuff way up in the stratosphere or higher where they are exposed to some very high energy sunlight, some very high energy ultraviolet radiation that we do not get down here on the surface of the Earth. And things start getting a little strange with some of that really energetic light, and you do get some odd numbered species up there. Some of those exist down here as well, but not nearly as common. Well, that finishes out the second lecture. I hope all of this makes sense. Make sure that you watch the videos that have the examples in there. And if you have any questions, make sure you contact me.